Hello, Physics in the Flesh is back with another waves problem. A cord of mass 0.60 kilograms is stretched between two supports 26 meters apart. If the tension in the cord is 140 newtons, how long will it take a pulse to travel from one support to the other? Okay, so the reason we say that there are supports is because this implies that we have two fixed ends. Okay, so essentially what you're dealing with is two stands, and you've got the string right in between them, and you've got a pulse traveling down. So maybe you twang the string, and then the pulse moves down. So you might have something that looks like this. Okay, and this pulse is going in this direction, let's say. Okay, we know the distance between the two supports is 26 meters, so you can insert that. And the next step is you want to identify what pieces of information you're given in the problem. For example, we're told the mass of the cord is 0.60 kilograms. The force of tension in the string, 140 newtons. The length of the string, 26 meters, and we're tasked with finding the time, how long it will take for the pulse to travel from one support to the other. So we're looking for delta t. So we're going to use two different equations to solve this and combine the two. And both of them are expressions for the speed of the pulse. Okay, the first one we're going to use is the relation between pulse speed, tension, and linear density. It's given by this formula. Speed is equal to the square root of tension in the string divided by mu. Now, this mu is the string's linear density. Okay, because it is a string, we consider it to be one-dimensional in this case. Okay, so string's linear density. Linear density, just like regular density, is mass divided by volume, but because we're saying it's linear, it's going to be mass divided by length. So we can actually rewrite this as square root of force of tension divided by mass over length. So this is one expression we're going to use. And the other is, well, we're looking for how long. This expression for speed doesn't have time in it. But we already know from our understanding of kinematics that speed is equal to distance over time. And if speed is equal to distance over time, and speed is also equal to the square root of force of tension over mass over length, we can equate these two formulas together and solve for our time. Okay, so based on this, speed is equal to distance over time. We can rearrange that and say, well, based on this, time is equal to distance over speed, right? Now speed, I'm going to use the expression over here and plug it in. So let's do that. So delta t is equal to delta v over the square root of ft over m over L. Okay, so it looks like a big expression, but all you really need to do at this point is plug in the values. So my delta d, your distance, is the 26 meters. Square root, force of tension is 140 newtons divided by, and you got another fraction in the denominator. Mass is 0.60 kilograms. Length is, again, 26 meters. Okay, this simplifies to, well, the denominator simplifies to 77.89 square root newtons over kilogram meters. Punch that in your calculator and you are going to get the time to be about 0.33 seconds. And that's how long it takes for the pulse to travel from one end to the other. And if you remember, based on the conceptual understanding of physics, the more tension you have in the string, the faster the pulse will travel. So that's it for this video, guys. Please smash that like button if you enjoyed it, and stay tuned tomorrow for my next video, 140 wave energy, to be posted at 12 noon. What? Wait, who's back to school? Pumpkin pie recipe. Okay, I'll save that for Halloween. Guys, so that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button and subscribe to Physics in the Flesh so you never miss a video from me, which, by the way, I post every weekday at 12 noon. So be sure to be on my channel at that time. Guys, as always, if you missed my videos from the past, be sure to click over there on the right. You'll see some of my latest videos there. And other than that, guys, I hope you enjoy the rest of your day. Peace.